Hello there and welcome to your tutorial presentation. This presentation is on first order linear differential equations and those differential equations which are reducible to first order linear equations. So before we look at an example, let's recall what we said the first order differential equation was. Recall that we said a first order differential equation could be written in its general form as dy dx plus py equals to q, where p is defined as a function of the independent variable x. So you must be careful there whether it's x or t, because independent variable can be t or x or any other relevant independent variable, depending on your situation. Also, on the other hand, q is given as a function of x. And in our discussing, we concluded that to solve this kind of equation, we needed what we call an integration factor, which here we're going to denote by r, and it's going to be a function of x, which is given by the formula r of x equals to e to the power integral of p of x with respect to x. So that is the formula for our integration factor as per our discussion. And then we also arrived at the conclusion that the solution to this differential equation will be given by the equation y multiplied by r of x equals to the integral of the integration of vector r of x multiplied by q of x. And then what you see here is that you'll end up integrating a product of two functions, which in this case suggests that your techniques of integration involving integration by parts will have to be at your fingertips, otherwise you're not going to win this case here. So you will have to integrate this integral, complete this integral, and you add your undetermined c. Then later find your y by dividing both sides by r to get an explicit expression of y in terms of x here. That's what we do. So that is all about the recall. Let's just get to the example, which is given here. Solve the following first order differential equation, which is given as dy dx plus 2y over x equal to sine x. In this case here, since we're not given initial conditions or boundary conditions, which means we're going to find the general solution. So in this case, let's rewrite the equation in a suggestive way, which is kind of make p and the q stand out in an easy way. So rewrite the equation as follows: dy dx plus 2 over x brackets y equals to sine of x. So as it has been written, it is easy to see that p, a function of x, is given by 2 over x. And the q, also a function of x, is given by the right hand side here, which is sine of x. And then our integration factor r of x is going to come as e to the power, the integral of p of x, which is in this case 2 over x, so our integration factor come to come as e to the power, the integral of p of x, which is 2 over x, so it ends up as 2 over x dx, which if we recognize that, we write that as e to the power integral 2 times the integral of dx over x. And we all know that this is going to give us e to the power 2 ln x. And simplifying that, we can see that this will get us to x squared. So now here's our integration factor. And then now resorting to the equation which gives us the solution, we said it should be y multiplied by the integration factor, in this case, which is y squared, equal to the integral of the integration factor y squared multiplied by sine x dx. So we can see we're in the presence of product of two functions here. Then we've got to apply our integration by parts. Then let's say u is equals to x squared, and u prime would be equals to 2x. And the v prime would be sine x, and the v will be n minus sine minus cosine x. So our v is going to be minus cosine x. And then multiplying here u and v according to the formula for integration by parts, we'll get here minus x squared cosine x plus, because there's a minus in the formula, with this plus minus here, we get a plus here, plus 2 the integral of x cos x dx. So again here we need to apply again the integration by parts. Then let's declare here our u to be equals to x, and our u prime equals to 1, and then v prime would be equals to cos x, which is a derivative of sine, then v will be then sine x. Then rewriting this, we have here minus x squared cos x plus, in brackets, we're going to have this multiplied by that, which will be x sine x minus the integral of sine x dx. That's what we're going to get there. And then now we need simply to carry out this integration, which can easily carry out by filtering in an integral sign to next to sine of x. Then we get that minus sine of x is a derivative of cos. Then that will integrate as cos. So then we have here minus x squared cos x plus 2x sine x, removing the brackets here. And the integral, you have agreed that is cos, then it's going to be plus 2 cos x plus c. So then what we have now here is simply y multiplied by the integration factor, which is x squared, equals to that. Then now we need to now make y substitute formula by dividing both sides by the integration factor. So carrying out the division, you get that y is equals to minus cos x plus 2 sine x all over x plus 2 cos x all over x squared plus c over x squared. So that will be our general solution. Since we're not given initial conditions, we'll leave that as that. So what is important here for me is to just recap the procedure which you follow so that you can actually revise this and then be able to go and carry out the examples. But my advice is, if you cannot reproduce this solution on your own without looking at my solution, then you are not ready to take examples which you have not seen before. The first thing is to start this example and make sure that maybe after looking at it, you think you understand it, you can pause a bit, and then after some time, just try to reproduce the solution as it is. Then after that, you can only proceed to doing examples, some of which I've given them here, and I've also posted them to you online. So I simply just try to solve some of the problems and give you the solution so that maybe you can try to find a way of working towards the solution. But what is important here is not the answer, but the procedure of solving these type of exercises. So that is that, I think, for the first order linear equation. Let's proceed to an equation which is reducible to first order linear. Now, let's say we're given is a problem which says solve the following initial value problem using an appropriate method. In this case here now, we're given initial conditions, which means we're not going to only end up at a general solution, but we're going to find a particular solution which is unique. Looking at this problem, I think we can all see that this is actually not a first order linear equation, but we can more or less rearrange in such a way that it more or less looks like a first order linear equation by doing the following. Let's suppose we subtract on both sides here 5, 5.7y on both sides. What we're going to end up here, we're going to end up with dy dx minus 5.7y equals to minus 6.5y squared. Now, if we rearrange, look at the left-hand side here, we can actually rewrite this as dy dx plus minus 5.7y equals to minus 6.5y squared. Now, if we actually, let's say, if we didn't have this y squared here, this equation would be linear. And the left-hand side actually looks like a linear, first order linear differential equation, where p of x will be this constant. But now, because of this, this is not a linear equation, a first order linear equation. This is what people sometimes call Bernoulli's equation, but I just refer to it here as a first order linear equation, which is reducible to first order differential equation, which is reducible to first order linear equation. So it is not a first order linear equation, like as you can see, equal to y squared. So, but it is reducible to first order linear equation by doing this kind of change of variable. Say, let's say here we're going to say let z, which is simply a helping variable here, let z be equals to y equals to 1 minus 2. I think in our discussion, we did this before, so it's not something new, which will give you that z is equals to y equals to minus 1. In this case, which means now you will have to rewrite this equation in terms of z. So for that, you need dz dx. So dz dx will be equals to minus 1 times y to the power minus 2 dy dx. I hope you are aware that I'm applying chain rule here. I applied power rule to this power minus 1 and then multiply differentiate the argument y to get dy dx. So that's what we have here. So now if you look carefully at this equation, you see that dy dx now is accompanied by this factor. And then in our process of changing this, reducing this equation to first order linear, we will have to consider this factor seriously and multiply the whole equation by it, which is going to give us the following. We're going to get here minus y to the power minus 2 dy dx plus minus 5.7 in brackets, and when we multiply this y times y to the power minus 2, actually it's minus, this is y times minus y to the power minus 2 is going to be equals to minus 6.5, because y to the power 2 and y to the power minus 2 is going to give us power 0, which is 1, and this sign is going to be a positive sign. Now simplifying on the right, on the left hand side here, this plus, this minus and minus will give us a plus. Then we'll end up with plus 5.7 times y to the power minus 1. But the y to the power minus 1 which you get here, y to the power minus 1 which you get here multiplying here, is our z there. And then which means this is dz dx like we have seen here. So we can rewrite the equation as dz dx plus 5.7 z, because this is y to power minus 1, which is z, equals to 6.5. At this point, you can see now we've got a first order linear equation. In this case, our first order linear equation, our p of x is identified as a constant function, which is 5.7. And our q of x is simply 6.5. And then our integration factor, a function of x, would be e to the power 5.7 dx, which simply integrates to e to the power 5.7x. That's what we have there. And then now our solution z will be given by this equation, which is z multiplied by the corresponding integration factor, which is e to the power 5.7x, equals to this integral of e 5.7x multiplied by sine x dx. So now again here we are faced with the integration by parts, and then we'll have to integrate here and then substitute this and then make z substitute the formula. Now let's do that. Let's simply take this integral as e here, as I, sorry, integral of e to the power 5.7x multiplied by sine x dx. So here we're going to take our u to be e to the power 5.7x, and our u prime is simply equal to 5.7 e to the power 5.7x. And then our v prime is sine x, and then our v is minus cosine x. Now we have to multiply that and that, which is going to give us minus e 5.7 x multiplied by cos x plus 5.7 integral of e to the power 5.7x multiplied by cosine x. I hope you understand why this sign is my plus here, because the formula has got a minus, and if we put a minus there, then we get a plus. Now we can apply our integration by parts here by taking the same u to be this and the derivative of that. So I'm simply going to take v here to be cos x, v prime to be cos x, and then v is going to be sine x. And now, so multiplying these two here, you're going to get e to the power 5.7x times sine x minus 5.7 integral of e to the power 5.7x sine x dx. We'll close that bracket there. I hope you can see that now we should stop integrating by continuing integrating this way, because here what has appeared here is our I, which we started with there, and we've got a negative sign here. So we can reorganize this as follows. Let's first of all remove the brackets here. What we're going to have here is equals to e to the minus e to the power 5.7x cosine x plus 5.7 e to the power of 5.7x sine x, and then here we're going to have minus 5.7x squared multiplied by I. And then now if we group the i's, this I and that I, we're going to have I in brackets 1 plus 5.7 squared equals to this integral, which is minus e to the power of 5.7x cos x plus 5.7 times e to the power of 5.7 plus sine x. That's what this is equal to. So now we need to make our I subject the formula, which then is going to remain as I is equals to this expression divided by this number, of course, plus c then. So now this would be the right-hand side of, remember our integration factor was e to the power 5.7x. So our z times e to the power of 5.7x is equal to this right-hand side. So that's what we have here. In this case now, we can now make z subject to the formula. But you recall that z is equals to y to the power minus 1. So what we can immediately do here, we can write this as 1 over y, and divide this side by e to the power 5.7x, and then we're going to get minus cos x plus 5.7x sine over 1 plus 5.7 squared plus c times e to the power minus 5.7x. And then this is what we've got here. I think what you can do there, you can actually now maybe simplify this 1 plus 5.7 to get a simple coefficient for cosine x here and sine x. I hope my calculations are correct. When I simplify this with this denominator here among these three functions, I get that here I've got minus 0.03 cos x plus 0.17 sine x plus c e to the power minus 5.7x. This is what 1 over y is. So now we can now simply say now therefore y, inverting both sides, remember this is over 1, inverting both sides, we're going to have here 1 over minus 0.03 cos x plus 0.17 sine x plus c e to the power minus 5.7x. And then this one will be giving us our general solution. That's what it is because of this c now. So now we are supposed to evaluate this at 0 because we're given here initial conditions that y at 0 is equal to 0, 5. So we now simply have to say y at 0 equal to 0, 5. This simply implies that if we evaluate this expression, we must get that equals to 0, 5. Now let's check what happens here. If we evaluate this expression at 0, we're going to get c here. So we've got here 1 over c from this, because this e to the power 0 is 1. And here sine at 0 is going to be 0. And the cos at 0 is going to be 1. And then which means here we're going to get C plus minus 0.03, and this must equals to 0.5 that. And then if we invert both sides here, and we know that, remember that 0.5 is half. So if you invert both sides, you're going to get that C minus 0.03 is equals to 2. And then, therefore, our C is going to be 2 plus 0.03, which simply simplifies to 2.03. That will be our C there. So I think we have arrived at our final answer, which is going to be Y equals to the following rational expression: minus 0.03 cosine x plus 0.17 sine x. Then you've got to replace this C by that, which is going to be plus 2.03 e to the power minus 5.7 x. That is going to be your particular solution, and that will mark the end of the exercise. I hope you notice what happened here. The key issue here is that you recognize that the equation is not linear, but of course you see that the right hand side is looking more or less like the first order linear equation. Then you must do the substitution which you saw here. You must do this kind of substitution whereby you say z is equal to y to the power 1 minus the power which you are given there. Then you get a y like this. Then you do the relevant kind of adjustment here, trying to find the derivative of z with respect to x. Then you transform that equation to linear, like we saw in this stage here. And once it's linear, then you follow the usual procedure of solving the first order linear equation. Then you say that you get to a general solution or to a unique solution, depending whether you are given the initial or boundary conditions. And then after this, I think you will be ready to now do some practice. And here are some of the exercises I gave you to practice with answers here to guide you what you are actually supposed to arrive at. Of course, there might be some mistakes in these answers, maybe typing mistakes, or they worked wrongly by myself, which is possible. That is not a problem, but you must try to master the method. And if there are some mistake which you can rediscover, that will point out that you have started learning. And for me, that is good enough. At this point, I would like to say thank you for listening. My name is Charles Suwasfani Msipa.